Hello! In this video, we're going to prove the following theorem. For every complex numbers a, b, and c, if c plus a is equal to c plus b, then a is equal to b. And if a plus c is equal to b plus c, then a is equal to b. Now, in this series, we're using a list of axioms for the complex numbers. These axioms come from MetaMath, and I'll leave a list of those axioms in the description below. So let's remind ourselves of what we're working with. We are given a set C called the set of complex numbers. We have a subset of the complex numbers R called the set of real numbers. And we are given three elements of the complex numbers: 0, 1, and I. We are given two binary operations on the set of complex numbers: addition and multiplication. So, given any two complex numbers a and b, a plus b is a complex number, and a times b is a complex number. And finally, we are given a relation on the set of real numbers called the less than relation. So, given any two real numbers a and b, it might be the case that a is less than b, and we write that like this. Otherwise, a is not less than b, and we can write that like this. And from here, we have a list of axioms for the complex numbers. Now, in proving this theorem, we are going to be using Axiom 4, which is the associative law of addition, which says the following. And we're also going to be using two other facts that we have proven to prove this theorem. We have proven for every complex number a plus 0 is equal to a, and 0 plus a is equal to a. We've also proven for every complex number a, there exists a complex number x such that a plus x is equal to 0, and there exists a complex number y such that y plus a is equal to 0. So now let's get into proving this theorem. To start out the proof, let's give ourselves three arbitrary complex numbers a, b, and c. From here, we're going to prove both 1 and 2. Let's start by proving 1. To prove 1, we're trying to prove if c plus a is equal to c plus b, then a is equal to b. So to prove that, suppose c plus a is equal to c plus b. Now, applying our third result, since c is a complex number, we know that there exists a complex number y, such that y plus c is equal to 0. I'm going to call this third result star. Now, we're going to establish a chain of equalities showing that a is equal to b. First of all, we know that a is equal to 0 plus a by our second result that we have here. Then we'll substitute 0 for y plus c. Then, applying the associative law of addition, we can move these parentheses around c plus a. Then, since c plus a is equal to c plus b, we can replace c plus a with c plus b. Then, applying the associative law of addition again, we move these parentheses around y plus c. Then, we know that y plus c is equal to 0, so we'll substitute that for 0, so we get 0 plus b. But then, according to our second result, we know that 0 plus b is equal to b. So this chain of equalities shows that a is equal to b. So a is equal to b. So that proves if c plus a is equal to c plus b, then a is equal to b. So we have proven 1. Now we're going to prove 2. To prove 2, we're trying to prove if a plus c is equal to b plus c, then a is equal to b. So to prove that, suppose a plus c is equal to b plus c. Now, applying star, we're going to apply it to c again. Right? And instead of attaining a y such that y plus c is equal to 0, we will obtain an x such that c plus x is equal to 0. And now we are going to establish a long chain of equalities showing that a is equal to b. So, by our second result, we know that a is equal to a plus 0 this time, Well, we're going to replace 0 with c plus x. Then, applying the associative law of addition, we'll move these parentheses around a plus c. Then, since a plus c is equal to b plus c, we'll replace a plus c with b plus c. Then, applying the associative law, we'll move these parentheses around c plus x. And then, since c plus x is equal to 0, we'll replace c plus x with 0. So we're left with b plus 0. And according to our second result, b plus 0 is equal to b. So this chain of equalities shows that a is equal to b. So a is equal to b, once again. So this proves if a plus c is equal to b plus c, then a is equal to b, which proves our second implication. So we've proven exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.